All right, welcome to part 2 of the section 1.5 video. We're talking about transformations of functions. We have so far seen that vertical transformations result in what are called outside changes. Okay, and I'll just remind you the general formula of a transformation of a function f that involves vertical transformations. Okay. I usually call the effects of C and D outside changes. Okay, and again they affect y coordinates. Okay, so in part A, g of x equals f of x minus 2. The graph of f is shifted down 2 units to obtain the graph of g. That's again a vertical shift down, and it only affected the y coordinates. So both f and g would have the same domain. H of x equals 2f of x. Multiplying f of x by 2 to obtain a function h of x is going to result in a vertical stretch away from the x-axis by a factor of 2. And that just, again, only affects the y-coordinates. To go from one graph to another, all the x-coordinates or the domain would remain the same, but all the y-coordinates are being multiplied by 2. And then part C, r of x equaling 2f of x minus 1. Okay. That would, to obtain the graph of r of x from the graph of f of x, you would multiply y-coordinates by 2, and then because of the minus 1, you would subtract 1 from y-coordinates after that. So it's a stretch of a factor of 2 first, and then a shift downward of 1 unit. But again, whatever C and D are, like in part C, capital C is 2, capital D is negative 1. And again, I like to call the effects of C and D outside changes. They only affect y coordinates. Okay, so scrolling down, we got all the way through example 3 in part 1 of the video, and we graphed 3 functions that were results of horizontal transformations of a given function f. Okay, and we'll just go through this again. G of x equals f of x minus 2. Okay, the graph of g of x was the graph of f shifted 2 units to the right. Okay, and it's just strange that it works that way. And we'll talk about why in just a moment. But again, when you see x minus 2, it's a shift to the right. If we would have seen x plus 2, the graph of g is a shift of the graph of f 2 units to the left. Okay. Then there was h of x. We graphed this. This was actually a horizontal compression by a factor of 1/2. Okay. And to get from the graph of f of x to the graph of h of x, you would multiply all the x coordinates by 1/2. And let me summarize this in just a moment, but there was also r of x, which was a horizontal compression by a factor of 1/2. And I'll just abbreviate horizontal compression by a factor of 1/2, followed by a horizontal shift 2 units right. Okay. So what you're noticing here is vertical transformations. The effects of C and D are multiply y coordinates by C and then add D to the y coordinates. But for horizontal transformations, which are going to have this form, we're going to summarize in just a second, f of a times x minus capital B. Now, the effects of a and b right here, these are what I like to call inside changes. Okay, and they only affect the x coordinates. So if you only had horizontal transformations, your domain is going to change, but the range of the function remains the same. Now, shortly we're going to be combining these two. I have one more example to do, but all horizontal and vertical transformations can be done at the same time. And if that's the case, then both your domain and your range would be affected. Okay, so let's look at the summary. Excuse me, forgot to pause before coughing. But let's look at a summary of horizontal transformations. Okay, now this is different again than in the textbook. This may be presented differently than in the textbook we are currently using. But, and let me zoom in. It's the Tidmore. There we go. Okay, so what does it say? Summary of horizontal transformations. For real numbers a and b, where a is non-zero. Now, capital A is going to be the scaling factor. If you multiply something by 0, it just makes the result 0. So since A is the scaling factor and it has something to do with multiplication or division, A is not allowed to be 0. And the graph of y equals f of a times x minus b, I'll rewrite it here in purple. Okay. And we're really just notice that what we're doing is we're varying our input with a composition in some sense, right? Typically we're starting with the graph of y equals f of x, and then we're varying our input to a times x minus b, which is really a composition. It's giving you a new function. Okay. Now notice that, and I'll highlight it or something. I'll use blue. Okay, so we've got in the expression y equals f of a times x minus b, okay, when we see a inside of those parentheses, we're really going to be scaling by the reciprocal 1 over a. And the absolute value is just to ignore the cases when a is negative, because in the second step, if a is negative, you would also do a horizontal reflection over the y-axis after you're scaling. Okay. Now, when the absolute value of a is between 0 and 1, since you're multiplying the x coordinates by the reciprocal, okay, so what's going to happen is, say, if a was 1/2, the reciprocal would be 2, and multiplying x coordinates by 2 doubles them and gives you an expansion away from the y-axis. Okay. If a is greater than 1, the horizontal scaling is a compression towards the y-axis. Okay. So, for instance, if a is 2, you're multiplying x coordinates by 1/2, the reciprocal. Making your x coordinates half as large is going to squish your graph or compress it towards the y-axis. Okay, step 3. We're still on the effects of a here. If a happens to also be negative, you're going to do a horizontal reflection, which is multiplying x coordinates by -1. Okay. So if you were looking at a transformation of one of our toolkit functions, a constant function, y equals x, the square root of x, absolute value of x, x squared, the reciprocal function, the reciprocal squared, whatever toolkit function that's been transformed, if you can tell it's been horizontally flipped at some point, that means a has to be negative. Okay? Alrighty. So, number 3, shift horizontal by absolute value of b units. Now, if you come back up to the top, I'll highlight this in orange. In my purple expression y equals f of a times x minus b, I'll just highlight b in orange. Okay, I want to connect the algebraic expression y equals f of a times x minus b to this verbal description of the steps that are happening. So whatever b is, okay, and notice it's always x minus b. So that general form of a transformation, you're always subtracting b. So for instance, if I had x minus 2, b would be 2. So Step 3 says shift horizontal by absolute value of b units to the right when b is positive. Okay, that would be the case where I had an x minus 2. B would be 2 and we shift to the right. And you shift by absolute value of b units to the left when b is less than 0. And what you're doing graphically is after you've done steps 1 and 2, you're going to add capital B to all x coordinates. And at the very bottom, I try to never be in this situation. But the note at the bottom, if instead the inside of the parentheses were factored, by the way, this is a typo right here. This should say f of capital A times x minus b. You would do the steps backwards. Oh, sorry, I just wrote the same thing I had before. I haven't had my coffee yet. There we go. So f of a times x plus b, only one set of parentheses. You would, again, do your shifting before you do your scaling. Okay. I try to just make sure I'm always matching the form that I wrote for you up at the top. Okay, so let's do another example. Where we're starting with algebraic expressions and we're going to go ahead and apply some sort of transformation. Okay, to that function. So I start with an algebraic expression for a function, describe the transformations. I should be able to find the algebraic expression or equation of the resulting function. Okay, we're going to come back and we're going to get to some examples where we do this graphically, but we're going to start here with working with algebraic forms or equations and then apply transformations. You can also start with the graph of a function and apply transformations to get a new graph. Or the last example I'm going to do, which is going to just be like a bonus or an extra, is I'm going to start with something that's already been transformed from a toolkit function and try and determine which transformations had taken place. But I'm getting ahead of myself. We'll start with algebraic forms. Okay, so find the algebraic form of a function g of x whose graph is the same as or the result of taking f of x equals 2x plus 2 and compressing horizontally by a factor of 1/2 and then shifted 3 units to the right. Okay. Now, if I was to come back up here, notice that in step number 1, whatever the factor is that I scale horizontally by, right? So if I stretch by a factor of 2 or compress by a factor of 1/2, that's the reciprocal of A. Okay, so if you look up at the general form of a transformation, it's f of A times x minus b. But what we're scaling horizontally by is the reciprocal, or has something to do with the reciprocal. So when I say compressing horizontally by a factor of 1/2, capital A actually has to be the reciprocal of that. Okay, that's the opposite of what happens when we do vertical expression. Sorry, I can't speak today. That's the opposite of what happens when we do vertical scaling. So either vertical compressing or stretching. There isn't this reciprocal relationship. Okay, and then it says shifted 3 units to the right. And whenever we shift to the right, you want to think of capital B as being positive. Okay, now g of x is a transformation of f, and it's 2 horizontal transformations. Remember, those are the inside changes, a and b, but g of x is going to be found by doing f of a times x minus b. Okay, so a is my green stuff in this case. B is the stuff that I have highlighted up in blue. And your first step is to not do anything to your value of f. So leave f alone, and we're going to replace a with 2 and capital B with 3. So g of x is f of 2 times x minus 3. Okay. Now, what does f do as a function? as a function, f of x is 2x plus 2, right? So basically, the outputs of f are 2 times whatever's in a blank plus 2. So, I'll highlight it, but this stuff here in orange is the input of my function. F is the function whose outputs are 2 times that input plus 2. That stuff's all going to plop right in this blank. So I'm going to also place the 2x minus 3 there. Okay. And what I'll do first, PEMDAS says maybe I should work when I simplify on the inside-most set of parentheses. So I'll distribute the 2. So I have 2 times in brackets. By the way, sometimes I like to use brackets instead of parentheses, especially when I have 2 sets of parentheses, or 3. So sometimes I'll use brackets just because that helps me. The brackets helps me see, or distinguish between the inside set of parentheses and the outermost set of parentheses. Okay, so 2 times x is 2x, 2 times negative 3 is negative 6, and then I still have the plus 2 on the outside. Okay, so again, I'll just trace the orange stuff I've done. So all 3 of those things in orange are the same. Going from my second equal sign that I just wrote in black to the next one, that's the step where I got rid of the f. Now, the very last step here would be to distribute the 2 into that set of brackets, or my outermost set of parentheses, and then add 2 when I'm finished. 2 times 2x is 4x. 2 times the 6, the negative 6 is negative 12, but then I have that extra 2 plus 2 on the back. I end up getting a 4x minus 10, and that is my g of x. Okay. So again, even with horizontal transformations, lines get transformed to lines. So I invite you to go to Desmos and graph both of these functions. You'll see that their graphs are both lines. Okay, let's do another example that's going to be a little more involved algebraically. It's going to be more work. So example 4, part B, we're going to start with the graph of a quadratic, or one whose graph is a parabola. In this case, h of x is 2x squared plus 4, and it's going to be stretched vertically by a factor of 2, reflected over the y-axis. There we go. Had to get the highlighter pulled up. Okay, so those first two, when you have a vertical stretch, that should say horizontally, by the way, folks. That is a typo. We want to stretch this thing horizontally by a factor of 2. Okay, my apologies. Okay, so we're stretching horizontally by a factor of 2, and then a horizontal reflection over the y-axis. So those are horizontal transformations. And then I'll highlight in blue, we're also shifting left 5 units. Now, we're looking for a graph. We're looking for the function g of x. That's a transformation of h of x equals 2x squared plus 4. So I'm going to start by writing h times... Let me back up. I need a little more room, so I got to write smaller. So I'm looking for a function that has the form h of a times x minus b. Okay. And I'll come off to the side, but... Okay, capital A is going to be the factor that takes into account the stretching by a factor of 2 and the reflection over the y-axis. Since we're doing a horizontal reflection, A is going to be negative. And then ignoring the negative, though, the value of A, whenever we stretch horizontally by a factor of 2, A is the reciprocal of our scaling factor. And then capital B... the last step is shifting left 5 units, so capital B would be a minus 5. Now, these two guys are going to, come and plug in over here. We're just going to be plugging negative 1/2 in for A and negative 5 in for B. Notice when for b, when we do x minus b, that would be x minus negative 5. Oops. That would be x minus negative 5. Okay, so g of x, we leave the h on the outside alone. We plop in the negative 1/2 for a. And then we're doing x minus b, which is negative 5. Okay, so we're subtracting a negative. So this ends up being h of minus 1/2 times x plus 5. Okay, now what is the function h? H of x is 2x squared plus 4. So the outputs of h are going to be 2 times whatever our input is squared plus 4. And I'll highlight that input in, let's see, maybe we'll do green this time. Oops. Okay, so in the previous step, we had simplified the input to negative 1/2 times x plus 5. That's what's gonna go in this blank in the next step, right? H is the function that squares the input, multiplies by 2, and then adds 4. So I get negative 1/2 times x plus 5. Now we're gonna square that, multiply by 2, and then add 4 at the end. Okay, so the square has to actually be distributed to 2 numbers here. Okay, we have to square the negative 1/2, and we have to square its multiple, x plus 5. So the 2 and the 4, those are just going to hang out on the outside. So I have 2 times, now negative 1/2 squared, you'll see is 1/4, and then I also have an x plus 5 squared, and then we have a plus 4 on the outside. The final step would be to multiply the 2 and the 1/4. 2 times 1/4 is 1/2 times the x plus 5 squared plus 4. And I'll leave the algebra as an exercise. This is a useful form of the function. It's actually an incredibly useful form in that this form gives you important information about the graph, which we'll talk more of when we talk about quadratic functions in a later section. But our function is 1/2 times, our g of x, the resulting function, is 1/2 times x plus 5 squared plus 4. And it will also be a quadratic function. Its graph will also be a parabola. And the result could be simplified further. You can check it on your own, and I implore you to do so for practice, but simplified, you get g of x equals 1/2 x squared plus 5x plus 33 halves. So that would be, I guess, a simplified form of g of x. The one that I've boxed in purple is what we actually call vertex form. And the one that I have boxed in orange, that's called the standard form. Okay, so now let's do some examples where we're putting everything together and combining transformations. All right, so a summary of transformations. Now, all I've really done to summarize the general form of a transformation and the effects of A, B, C, and D is I have literally just taken the 3 steps from the summary of horizontal transformations, and I have added on the 3 steps in my summary of vertical transformations. Scroll down to the bottom. So all the steps together, there would possibly be 6 of them. If we were talking about a resulting function whose equation was, I'll highlight it, y equals c times f of a times x minus b plus d. Okay, so just so you all are aware, A, B, C, and D, oh, sorry, it actually just says this right on the top. A, B, C, and D are just all numbers, and A and C are non-zero. Those are scaling factors, and multiplying by 0 would just be silly. Okay? So we're starting with those 4 real numbers, A, B, C, and D, and those are the values that tell us which horizontal and vertical transformations are taking place. And if we have a function f, and also just know that the input variable is x. But the graph of y equals c times f of a times x minus b in parentheses, and then outside the function, we have a plus d, and that's obtained from the graph of y equals f of x by performing the following transformations in the following order. So this is where I took a departure from the book that we currently use. I like to use A, B, C, and D because it gives me a natural order of, it gives me the order naturally of the transformations that I would be applying. Okay. So everything is basically the same. So you can read through the summary. Again, I want you to compare horizontal scaling is by the reciprocal of A, but vertical scaling is just by C itself. Right? So you'll see for horizontal scaling, you multiply x coordinates by the reciprocal of A, 1 over A. The absolute value just ignores the negative. And then, step 4, if we do a vertical scaling, it's just by C. We multiply the y coordinates by C. There is no using any reciprocals. So I'm going to go straight into an example, and we'll do an algebraic one here. I'm going to have to downsize my screen a little bit. There we go. So I'm going to start with a toolkit function. Okay. So remember, the toolkit functions were in the first section of our book, at the end of the section before the exercises. So I want to find the algebraic form of a function g of x, whose graph is identical to the graph of h of x equals x squared, but it has been transformed in the following order. Okay, so we're saying g of x is a transformation of our toolkit function h of x equals x squared. Okay, so let's look at these transformations as they're being described one by one. So notice the first one is a compression horizontally by a factor of 1/3. Okay. Now I'll write this down on the bottom. Actually, since g of x is a transformation of h, g of x would have the form c times h of a times x minus b with a plus d on the back. Okay, so our goal is to find a, b, c, and d from the list of transformations, and then eliminate the h by using the fact that h of x is x squared. And by the time we're done, we're just going to have an equation with only numbers and a variable x in it. Okay, so back up to the top. I've highlighted the first step here. It's horizontally compressed by a factor of 1/3. That has to do with capital A. And if you look back at the steps, the value of A and the scaling factor are the reciprocals of each other. Now, there's no horizontal reflection after that compression, so in this case, A will be a positive 3. Okay, next step, we have a shift left 1 unit. Okay, well, if we're shifting left 1 unit, that means B has to be minus 1. So B is negative for shifts left, B is positive for shifts right. Okay, moving to the next one, we have a vertical compression by a factor of 1/2, but notice we're also doing a vertical reflection in the next step. So that means capital C has to be negative, but here we don't do the reciprocal like we do for A. If we're compressing vertically by a factor of 1/2, C is 1/2. And finally, the last one is our compression or shift up 4 units, which I just highlighted in purple. When you shift up, D is going to be capital 4. When we shift up, D is positive. When we shift down, D is negative. Okay, so g of x now would be, let's see, c is 1/2, h we leave alone, a is 3, and then we have 3 times x minus b. B is -1, so I'll skip a step. X minus -1 becomes x plus 1, and then I have a plus 4 on the back. Okay? So my next step, everything's going to be the same. I have a -1/2. Now, h is the function that takes its inputs and squares them. Okay, but after h of 3 times x plus 1, we still have a plus 4 on the back. And I've just done this several times. The input of h is 3 times x plus 1. And, okay, h is the function that takes that input and then squares it. So I'll underline it, but this entire h of 3 times x plus 1 is just the 3 times x plus 1 squared. The next step, we could distribute the square. So now g of x would be -1/2 times 9 times x plus 1 squared with a plus 4 on the back, which is going to be equal to negative. So multiplying the -1/2 times the 9, I get -9/2 times the x plus 1 squared plus 4. And again, I could leave it in this form, or I could square the x plus 1 and distribute the -9/2 and add like terms and write it simplified. But there's our, that's the function g of x that's been formed from h of x equals x squared by performing our transformations in that order. Okay, so one more graphical example, and then I might do a bonus example, or I might wait until class to answer some questions, but let's take a look at another one. Okay, so here we go. We're going to start with the graph of a function, f of x, and we're going to draw the graph of the function, and I'm going to rewrite it just so that I have a little more space to work with. G of x is -2 times f of 2 times x minus 1 plus 1. Okay, and we are going to take the graph of x on the left, graph of f of x on the left, and sketch a graph of this function g of x. And apparently I'm kind of dyslexic today. What I wrote was g of x is on the right. Now we're going to go through here and we're going to identify some values like we usually do. So I'm going to start with the inside changes, and I'm going to highlight +2 in orange. That's going to tell me that capital A is 2. Okay, so as a matter of fact, it's not even a bad idea to just compare this thing to your general form, right? The general form of a transformation of f would be CF of A times x minus b plus d. Okay, so I just highlighted A, and I just highlighted the 2 inside the parentheses and the A inside the parentheses in the general form, and that tells me that capital A is 2. Okay. Now we have the -1. Okay. And also that's matching up with x minus b, so you'll notice I have 1 and b highlighted in blue. So we know that capital B is equal to 1. And then we have a capital C. Let's see if yellow shows up. Okay, I think it does. So you'll notice that in front of the F we have -2. That becomes our capital C. I don't know if yellow pen's going to show up very well. Hopefully y'all can see the C equals -2 in yellow. And as a matter of fact, maybe I'll just do the last one here in red. The +1 on the back is the same as the plus D in the general form. So D is actually +1. Okay. Now, in terms of transformations, capital A being 2, that's actually a compression by a factor of 1/2. So I'm going to say horizontal compression by 1/2. So what we're going to do is we're going to multiply x coordinates by 1/2. Okay, b equals 1. What that's going to tell us to do, that's actually a shift right 1 unit. Okay, so we're going to add 1 to x coordinates. I lost some room here. I'm going to actually write c equals -2 in black just because it's hard to read in yellow. That's actually going to be a vertical stretch by 2. Okay. And then followed by a vertical reflection. But we're going to multiply y coordinates by -2. And then capital D was equal to 1. So that's a shift up 1 unit, and that's just by adding 1 to the y coordinates. Okay. So horizontal compression by 1/2 because a is 2, so we multiply x coordinates by 1/2. B is 1, shifting right 1 unit is the same as adding 1 to x coordinates. C is equal to -2, vertical stretch by a factor of 2, followed by a vertical reflection because it's negative, but in terms of coordinates, we multiply x by -2. Sorry, we multiply the y coordinates by -2. That's an outside change. Capital D is 1, shifting up 1 unit, adding 1 to the y coordinates. So what we're going to do in the bottom left, the way that I like to accomplish these transformations, is to make a table of values of special points that I'm going to transform from a graph. Now, a line only needs 2 points to be transformed. A parabola needs 3 points to be transformed. Okay, so depending on which graph you're transforming, that's going to determine how many points you're going to use. Now, I'm going to use the endpoints of each of the 3 line segments just like I did in my first and third example. and the x and y coordinates are -2, -2 of the farthest leftmost point. The next point has coordinates 0, 2, and then it's 2, 1, 4, 1. Okay. Now I'm going to create 2 more columns going to the left, and two more columns to the left of x and 2 more columns to the right of y. Okay. Now, moving to the left, the value of a only affects x coordinates. So in that next column, you'll see above I wrote a equals 2, but we actually multiply the x coordinates by 1/2 to get -1, 0, 1, and 2. Okay. And then b is equal to 1. So after we multiply x by 1/2, we add 1 to those x coordinates. So the last column would be the 1/2 x's that I just found plus 1. So I'd get 0, 1, 2, and 3. And that was the effect of b being +1. Okay, now the next column to the right of y, we're going to do the effects of c first. C is -2, so we're going to take -2 times the y coordinates to get -4, 4, 2, and 2. And then d was +1, so I'm going to take those previous -2y values that I just found and add 1 to them. So -4 plus 1 is -3, 4 plus 1 is 5, 2 plus 1 is 3, and another 2 plus 1 is 3. And now, these are the x and y coordinates of the graph of G. So we'll plot those, and I'll do it in purple. We have the point 0, -3 on the graph. We have the point 1, 5 on the graph, so 1 to the right, 5 up. We have the point 2, 3 on the graph, so 2 right, 3 up. And we have the point 3, 3 on the graph, which is 3 right, 3 up. And we'll connect all of those points with line segments, right? Line segments get transformed to line segments. You can see the effect of the vertical stretch going up 2 units. So I actually just caught a mistake, right? Because I said there's a vertical stretch by a factor of 2, but C was negative. There was supposed to be a vertical reflection. And the graph, what I just graphed in purple, has the same general shape as the graph I started with in black. They should actually look kind of upside down of each other because there's been a vertical reflection. So I actually have to step back. So y'all might have actually caught me in this mistake, but you're going to notice that I'm going to erase the effect of the y-coordinates that I just had. And actually, I was supposed to multiply all my y-coordinates by -2. -2 times -2 is actually +4. 2 times -2 is -4. 1 times -2 is actually -2. And then I can add 1 to those. 4 plus 1 is 5. -4 plus 1 is -3. And then both those -2's plus 1 would just give me 2 -1s. Those were actually supposed to be my y-coordinates. So I forgot to take into the account of the reflection. I multiplied by 2, but I didn't multiply by the negative. So actually we have the point 0,5 on the graph. We have the point 1, -3 on the graph. And then we have the point 2, -1, and 3, -1. There we go. So you can see that this graph is twice as tall as the one in black, the one that's in purple. That's the stretch, moving you away from the x-axis. It's half as wide. A was 2, so we compressed the graph by a half, so it's half as wide. And then there was some shifting that went on, and there's a vertical reflection. Okay, but my graph... and I'm sorry if I repeated myself. I might have accidentally paused the video, but this graph is twice as tall, half as wide. It kind of looks upside down of what f of x was. And then there's been some shifting, but in purple is the graph of g of x, and in black is the graph of f of x. Okay, I'm going to stop there. I might post one more video with one more example, but we'll talk more about these in class. Thanks for tuning in. I know the videos for this section were long, so thanks for bearing through them. Anyways, take care, have a good rest of your day, and until next time.